Magnetic field force between two current carrying wires. Force between two parallel wires. Set up two current carrying wires, each of length L, next to each other. Okay, so let's just start with that. Here's wire 1. See how the current I1 is going that way? Here's wire 2. They're parallel, and that's going that way. Each wire will generate a magnetic field. Now what happens if this wire is generating a magnetic field and this current carrying wire is within the field? It's going to feel a force. So let's start with finding the force on wire 2 due to wire 1. Well, we go back to our equation, and it's B1 equals mu 0 I1 over 2 pi d. That's the magnitude of this field, B1, at this distance here, d. And notice how all along this wire it feels the exact same field because it's at the same distance. You can see how the field's going down. So let me just read this again just to make sure, because we want to stay up with this. The wires are separated by a distance d. The magnitude of the magnetic field generated by this wire that is over here near I2 is B1 is mu 0 I1 over 2 pi d. And that's the equation we gave last chapter for the magnetic field due to a current carrying wire. The magnetic field due to wire 1, here's the magnetic field due to wire 1, and if you look at this right here, this vector here, it's perpendicular to I2. So when I use the force on wire 2 due to wire 1, that would be I2, the current I2, times the length of wire 2 times the magnetic field due to B1. And since B1 is perpendicular, I can use the full value. Now I just found B1 on the previous slide. Okay, we found it was this. This is the magnetic field of wire 1 in the vicinity of wire 2. So I just plug it in. Now this doesn't look very elegant, so I'm just going to rearrange it a little bit so you can see some symmetry here. The force that wire 1 exerts on wire 2 is mu 0 I1 I2 over 2 pi d times the length. This is the length of the wires. We can do the same algebraic technique to find the force that wire 2 exerts on wire 1, or we can just invoke Newton's third law. It also works for magnetic and electrical forces, just like mechanical forces. And we will state that the magnitudes of the two forces are equal, and here are the magnitudes, and notice I show the vector notion of the forces, and their directions are opposite each other. Now we have to find out what is the direction of the force. Are the wires attracted or repelled? For example, you could have equal and opposite forces like that, according to Newton's third law. That's valid. Or the forces could be like this. Newton's third law is not telling us which ones they are, so we have to use another technique to find that out. If we want to find the force on wire 2 exerted by wire 1's magnetic field, we have to find out what direction the magnetic field is over here due to wire 1. Use the right-hand grip rule. Put your thumb in the direction of I1 and then curl your fingers about the wire, and you'll find that your fingers go into the page like that. So we now know that the magnetic field to the right of wire 1 is into the page. Now let's just get rid of this so we're not even thinking about that. Try and simplify. We now have a current in a magnetic field. We use the right hand rule. We put our entire hand, all our fingers pointing up. Then we curl our forefingers into the page, into the magnetic field, and we stick our thumb out. And which way is our thumb pointing? To the left. So the force that 1 exerts on 2 is to the left. We now want to find the force on wire 1. So what kind of magnetic field does wire 2 generate in this area? Use the right hand grip rule, thumb in the up direction, curl your fingers about the wire, and you find that on this side you have a magnetic field coming out of the page. Like we did on the previous page, the wire has done its job, we get rid of it. Now I use the right hand rule and I put my hand, my 4 fingers and thumb in the direction of the current. I curl my fingers out of the page and then stick my thumb out, and I find out that the thumb points this way. So remember, wire 1 is feeling a force in this direction, wire 2 is feeling a force in this direction, and they're the same magnitude, of course. So what we have is wires with parallel currents in the same direction attract. That seems odd, right? Because normally when we had a positive and a positive pole, they repel, a positive charge and two positive charges repel each other. But in this case, if the current's in the same direction, the wires attract. But what if the currents are in opposite directions? You probably already can guess the answer, but let's work it out anyway. Let's start to find the force on I2. Use the right-hand grip rule for wire 1. Magnetic field will be into the page. But now, when we look to find I2, the current is in the opposite direction, so when we use the right-hand rule, we find that the force is to the right. So you can start to see what's happening here. To find the force on wire 1, we use the right-hand grip rule for wire 2, and in this case we find the magnetic field is into the page. So now when I use the right-hand rule to find the force on I1, I find that the force is to the left. So wire 1, the force on wire 1 is to the left, the force on wire 2 is to the right. So what we have, which is what we guessed hopefully, is wires with parallel currents in the opposite direction repel each other.